Hello everyone, I am Filippo Barbari from the University of Bologna, and today I will talk to you about my project, number 2221, Designing Scientific Applications on GPUs, which I developed in the University of Luxembourg. My project consisted of the CUDA implementation of the libRSB library. The libRSB library is a library which was implemented around 2010 by Dr. Michele Martone of the University of Rome, and he has invented and implemented this recursive sparse blocks format, which is a cache-efficient and parallel algorithm to perform the most common sparse matrices operations. For example, here we have the SPMV, which is a multiplication between a sparse matrix and a dense vector. Let's go into the details. Recursive sparse blocks is a hybrid matrix storage format, which combines three different storage formats together at different levels. At the highest level, we have a Z-Morton sorting of blocks, and for blocks, I mean the submatrices. At the intermediate level, the blocks or submatrices are recursively subdivided into a quad tree structure, and at the end, at the leaf level, in the lowest level of the structure, each submatrix or block is stored with the standard COO, CSR, or CSC sparse matrix formats. The Z-Morton is a special kind of space-filling curve, like, for example, the Hilbert's spiral, which helps preserving the spatial locality of data points. Because when multiplying two matrices together is really important to find the neighbors, non-zero elements of the matrix, to continue with the algorithm. In the figure aside, we can see an example of this Z-Morton sorting. Then the quad tree data structure is a quaternary tree often used to subdivide a continuous b-dimensional space to optimize the b-dimensional range query. The RSB uses this format, this data structure, to look for the closest non-zero element and to subdivide and memorize the blocks of a sparse matrix. Here we have an example of the subdivision, recursive subdivision of a continuous space. And this is a heuristic that the library implements to decide whether to further subdivide a given submatrix or not, based on this estimate of the memory that will be required to store a given block into CSR in the first line or COO format in the second line. Now let's go into these matrix storage formats. The first one, and also the simplest one, is the COO, which stands for coordinate list, which simply represents a matrix as an array of triplets, each one having the row index, the column index, and the value of the element. Here we have a simple example. The matrix on the left is stored as COO, as shown on the right. Then we have CSR, which stands for compressed sparse rows, which works the same way of COO, but is an improved version of it, because it tries to compress contiguous adjacent row indices by memorizing the indices in the column index array. For example, the same matrix as before requires now one less row index if using the CSR format. Then we have the CSC format, which works the same way of CSR, but exploits the column major sorting. And here we have the same example. Then let's go into the implementation. My implementation work is mostly focused on the translation into CUDA code of the most common matrix allocation function, which was a translation between a COO formatted sparse matrix into a RSB formatted matrix. And I used the CUDA unified memory to help me in this work. And then after that, I started implementing the SBMV algorithm, especially translating it into a CUDA kernel. Unfortunately, at the time of this recording, there's a memory issue in the CUDA kernel, so I'm not able to show you any results, but I will fix this issue in the future. And as conclusions, let me say that this library has really great potentials because of the wide range of possible use case scenarios and it has proven its performance and efficiency in many cases, as it's shown in the papers. But if you look at the numbers I put below it, this library is really big, is really huge, and trying to extend it would require much more time and manpower. And that's it from me. Thank you for your attention.